Part A asks to show that cosine of 105 degrees is minus q given that cosine 75 degrees is q. We can draw the unit circle to show what the angle 75 degrees looks like. At 75 degrees, the cosine value is q. Now we can draw cosine 105 degrees. Cosine 105 degrees can be rewritten as cosine 180 minus 75 degrees. This will let us see that the acute angle is still 75 degrees. The angle 105 degrees is in the second quadrant, so it will have a negative value. Therefore, cosine 105 degrees is minus q because it has the same cosine value as cosine 75 degrees, but is in quadrant 2. Quadrilateral ABCD is inscribed in a circle with radius r and circumference AC. BC is also of length r, AD equals CD, and the angles D and B are right angles. Part B asks to show that the angle BAD is 75 degrees. Triangle ADC is both an isosceles and a right triangle, so we know that each of the other angles that are not the right angle is 45 degrees, because we know that they have to be equal and add up to 90 degrees. To find the angle BAD, we're still missing the value of the angle BAC. We can find this by using the sign of the angle BAC in the right triangle BAC. So this means BAC is 30 degrees. We can then add the angle DAC and BAC together, and we get 75 degrees. And this is the value for BAD. Part CI asks to consider the triangle ABD and to show that the side BD squared equals 5r squared minus 2r squared q squared root of 6. Whenever you see an equation involving sides of a triangle that are being squared, there's a high chance we're hinted to use the triangle cosine rule. This is found on page 6 of the formula booklet. We can now substitute the generic variables in the formula with side names relevant to our question. We're trying to represent BD squared, so we will write this instead of c squared in the formula. Our angle is 75 degrees because the angle BAD is opposite the side BD, which represents side C. Let's now consider side AD and see if it can be represented in terms of r. I will represent side AD with x for now. If we use the Pythagorean theorem, we get r squared root of 2. Now let's see if we can do the same with the triangle BAC. After applying Pythagoras, we get r squared root of 3 for the side AB. We can now substitute these values for AD and AB into our expression that we wrote for BD squared. We can simplify some and then deal with the cosine 75 degrees. The answer doesn't have cosine, but instead has q. If we recall from part A, cosine 75 degrees was represented as q. So we can just substitute this in. Part CII asks to find a different expression for BD squared in terms of r and q when considering the triangle BCD. We can use the cosine rule again. We already know the side BC is r, as this was given to us, and DC is r squared root of 2, as it is the same as side AD, which we already found in the previous part. The angle in question here is BCD. This can be found from the summation of the angle ACD, which we already know to be 45 degrees, and the angle BCA. It can be found by subtracting 90 and 30 degrees from 180 degrees. So we get 60 degrees. To find the cosine, we can use the property from part A again. 60 plus 45 degrees is 105 degrees. And we know cosine 105 degrees is minus q. So here we got another expression for BD squared. Part D asks to show that cosine 75 degrees is 1 over square root of 6 plus square root of 2. We already know that cosine 75 degrees is q. And we also know we have two equations from CI and CII that use q. Both of them have one side that equals BD squared. We can use a transitive property to equate the right-hand sides of the two equations, and then solve and isolate for q. In the end, we get that q is 1 over square root of 6 plus square root of 2. And we can just substitute cosine 75 degrees for q, and we have the answer. So that's it for this video. Thank you for watching. I hope I helped with this question. Please like and subscribe. Bye!